So today we're going to the back of the notes in B11 and B.12. I think we'll get to that on Wednesday. But this is a section on vector and matrix norms. And so we just want to cover this material before we get into chapter 5 in the notes, because chapter 5 will need this information.
Is that B11?
Yes, B.11. If you look in the index of the notes, I think it's at the very end of the of that textbook. All right, so when we're talking about vector norms, well, if we have vectors x and y, which are and they're length 1, then they're just scalars. So the most natural way that we look at distance between x and y is just the absolute value of their difference, right? So if these are length 1, then their distance can just be described by this absolute value, right? The distance between these two. We want to look at a similar property, but for vectors instead of these being scalars. We'll talk about a vector norm. So this is a vector norm. It has the following properties. So we have 3 properties for vector norm. First of all, the norm is always greater than or equal to 0, and it's 0 if and only if the vector itself is a 0 vector. So that's the first property. So, and we'll see this too. It'll we'll see it naturally when we look at the definition of the norm. So that's the first property. The second property is we have a scalar times a vector, then we can just pull that scalar out and have the absolute value of it times the norm of the vector. And this is for any vector x and any scalar alpha. Okay, so that's the second property. And the third property of norms is if I have one vector, the norm of one vector plus another vector, it's less than or equal to the norm of x plus the norm of y for all vectors x and y. And so this last one is what we call the triangle inequality. Okay, these are the 3 properties of vector norms, and now we'll talk about the most common vector norms that are used. Alright, so the most common vector norms belong to the family of P norms, or sometimes they're known as LP norms. So P norms can be defined like this, because we have several different types of norms, and we'll discuss properties of each one, but overall This is the definition for a p-norm. So for I equals 1 to n, it's the sum p to the 1 over p power. So p can be a variety of things, and we'll discuss each one, but it can be shown that for any p, greater than 0, then the p norm defines a vector norm. So the p norms that we want to look at here are the 1 norm, the 2 norm, and the infinity norm for vectors. So those are the 3 ones that we're interested in looking at. So first of all, if p equals 1, that's the L1 norm. And it's just the Euclidean distance. So, I'm sorry, it's not. I was going on to the L2 norm. The L1 norm is defined this way. So it's just the sum of all of the absolute values. So that's the L1 norm. And then if we have p equals 2, that's going to be the L2 norm. Now this one is just the Euclidean distance. So 2. These are vectors. So we have the square root of the sum of the squares. Xn squared. Now, does anybody know what this looks like here? If I had the square root, then what is all of this under here? The sum of the squares. If I'm thinking about a vector, like vector multiplication, what would that be? Just x transpose x, right? So we have the vector multiplied by itself, so we have the transpose. So this right here is an inner product. So the L2 norm is equivalent to the square root of the inner product of that vector. And this is something that we'll use. So if I want to talk about how the 2 norm relates to the inner product, then I could say the 2 norm squared is equal to the inner product of x with itself, right? Okay, so this is something that we use to generally, or it's generally used to prove or help prove different things. So it's just a useful thing to keep in mind in your bag of tools. Alright, so that's the L1 norm and the L2 norm. And then finally, the last one that we're going to discuss for vector norms is the infinity norm. And the definition that we have for the infinity norm the maximum from I equals 1 to n of xi. So it's just the maximum absolute value in your vector. So whichever is the largest, we take the absolute value of it. So these are the 3 norms that we'll use and we're going to talk about in this section. Alright, so now we'll just do a simple example of finding each type of norm given a vector. So I have my vector x, 1, 2, negative 3. So if I want to find the one norm, what would that be based on the definition? Right, because we have absolute value of 1 plus the absolute value of 2 plus the absolute value of negative 3 equals 6. Okay? So if I want to find the 2 norm based on the definition, what would I have there? Square root of 1 squared plus 2 squared plus negative 3 squared. So we get the square root of 14 for this one. And then lastly, the infinity norm. So it's going to be the maximum.
It's 3.
Right. So the maximum of these 3 elements, or the absolute value of those, which is just 3. So that's just a simple example of how to find each of these vector norms. So we've got room right here. I think I'll come over here. All right. So now what we're going to talk about is an inequality that is used a lot throughout this course and various other courses. I mean, I've used it in several different classes, and so it can be shown that the L2 norm satisfies, and here in the notes, and I think it has 2 different names. The first name is Cauchy-Bunyakovsky-Schwarz inequality, but most of the time I hear it referred to as the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality is this. So if I have 2 vectors, x transpose y, then that's going to be less than or equal to the 2 norm of x times the 2 norm of y. So this is a good inequality to remember, and this is for any vectors x and y. Because it's very useful. So it is actually a special case of the Holder inequality. That's defined by this. So I have x transpose y less than or equal to, and so this is just with the p norms, p and q, where 1 over p plus 1 over q is equal to 1. So we will prove the Cauchy-Schwarz inequality for vectors in Rn, and the proof that can then be generalized to a complex vector space. So let's go ahead and take a look at that now. Okay, so I said, the proof can be generalized to a complex vector space. So, let's see. So we have for x and y and Rn, then we have a constant c in R. And y not equal to 0. So I'm going to start out, instead of just having, okay, yeah, so I'm going to start out with x minus cy transpose x minus cy, right? And this is equivalent to the 2 norms squared, just as we talked about how x transpose x was equal to the 2 norms squared of that vector. So this is our vector here, x. So that's the 2 norms squared. And we know this is greater than or equal to 0 by the definition, or by the properties of the norm. So now let's just take a look at this greater than or equal to 0. Alright, and that follows from the property of inner product. So now what I'm going to do is just go ahead and multiply all of this out. The transpose would come to each of these in here. And when we multiply it all out, we get x transpose x minus x transpose cy, the cy, then minus cy transpose x plus cy transpose cy. So now to simplify this a little bit, this right here is equal to what? X transpose x.
Square root of the 2 norms? Or
the 2
just
norms
the 2
squared. Right. The 2 norms squared, because we have the
square
square root
right,
of
right.
yeah. So that's the 2 norms squared. And then we can combine terms here, 2x. Oh, and I'm going to pull the c out too, because it's a constant. So then we have x transpose y. And then we have c squared right here. So c squared comes out, and then I have y transpose y, which is equal to
y, the 2 norms squared.
Right. Okay. So now that we've arrived at this is nonlinear. So what we can do is we can try to find a value of c that minimizes this expression when we differentiate with respect to c. So alright, so we're going to differentiate with respect to c. When we do that, this term goes away. Here, this becomes constant, and this becomes linear. So this is going to be negative 2 x transpose y plus 2c and then we still have the 2 norms squared. There. So we're trying to find a value of c that minimizes this expression. So after we do it, right, we set it equal to 0. So after we've differentiated, then we just want to set it equal to 0. And we want to find where the minimum occurs at, so we just want to solve for c. Alright, so when we solve this for C, we get C is equal to 2x transpose y over 2 times the 2 norm of y squared, right? Yeah, and then our 2's just cancel. So this is x transpose y over the 2 norm of y squared. So that's the unique value of C that minimizes this. And if we go back here and plug in this value of C, then we can proceed from there. So it's going to get a little bit messy now, but so going back to this inequality right here. So we had 0 less than or equal to. So it's 2 norm of x squared minus 2. And I'm going to put brackets around this whole expression. X transpose y over the 2 norm of y squared times x transpose y. And then in this last term, we have c squared. So it's x transpose y over the 2 norm of y squared, quantity squared, and then times the 2 norm of y squared. So now that we've plugged in c, we just want to try to simplify this expression a little bit. So what we have here, I've got x transpose y, so I could rewrite that as x transpose y squared in the numerator here. So I have x transpose y squared, I don't need this bracket anymore, over the 2 norm of y squared. And then here, what we can do is we've got x transpose y squared in the numerator. And in the denominator, we would have, I'm going to write
2 norm of y.
To the 4th power.
Yeah, then that cancels. And
Right, so we have this in the numerator. So what ends up happening is we've got the 2 norm of y squared over the 2 norm of y to the 4th power. So we don't need a different expression now. So it's just going to have the 2 norm of y squared in the denominator there. So now let's take a look at this. And what we have. So we have minus 2 x transpose y squared over the 2 norm of y squared plus 1. So one of these cancels out, and then we have the 2 norm of x squared minus x transpose y squared over the 2 norm of y squared. And now what we're trying to show here, and that's all greater than or equal to 0, is we're trying to prove the Cauchy-Schwarz inequality. So we almost have, we have all the components for it now, we just need to get it in the right order. So the Cauchy-Schwarz inequality has x transpose y on the left-hand side. So let's go ahead and move that over there as that whole expression. So we have x transpose y squared over the 2 norm of y squared, and that's less than or equal to the 2 norm of x squared. So then I can just multiply both sides by the denominator here, and I'm going to come over here. So then we have x transpose y squared less than or equal to 2 norm of x squared times the 2 norm of y squared. I think I might have gone off the board a little bit. And then if we take the square roots of both of these sides, then we'll arrive at the Cauchy-Schwarz inequality, which is what we were trying to get to. So now we've just proven the Cauchy-Schwarz inequality. Are there any questions about anything here?
Way back in the years, how did you get minus 2c x transpose y from those two?
From these two right here? Well, even though this is x transpose and this is x, they're the same vector, so we can consider them like terms and go ahead and combine them together. Is that what you're talking about? Those two right there? The vector x transpose and x are the same vectors. They just, one is a row and one is a column. So that's why we consider them to be the same and go ahead and combine them here in this way. We just, sometimes we have to put a transpose on it to do multiplication, otherwise the vector multiplication wouldn't be defined. But they're still the same vector, and y is the same vector, and c, well, c is just a scalar. So that's how we can combine those. Okay. Any other questions right now? Okay. All right. Okay, so now that we've talked about the various notions of the size or magnitude of vectors, we can discuss distance and convergence. So if we're given a vector norm for two vectors, x and y, then we define the distance between the two vectors. Yeah, that's not we define the distance between these two as just the norm of their difference. So this is how we find the distance between two vectors. Now what we want to do is define convergence of a vector. So we say that a sequence of vectors, converges to a vector x if the limit as k goes to infinity of the distance of these two vectors is 0. So what this is saying is as k goes to infinity, so as we get a new vector each time, the distance between these two gets smaller and smaller, and that's how we check for convergence. And that's a typical method of checking for convergence anytime in code or things like that. You just want to check the distance between your new iterate and, your new iterate and your old iterate. And if the distance is getting smaller and smaller, then you're converging to a solution. And this concept will be important when we get to iterative methods, because instead of doing all this work like in Gaussian elimination to finally arrive at a solution, we'll start with a really approximate solution, sometimes just an initial guess, and then we'll check to see if our iterates are converging to the actual solution or not. So this is the idea behind convergence of vectors. So the distance between this and this is going to be approaching 0. And it can be shown that regardless of the choice of norm, then x is going to converge, or xk is going to converge to x if and only if each component, so this is the ith component of xk is converging to the ith component of x. So that makes sense naturally if the whole vector xk is converging to the vector x, then each component, or each corresponding component, will be converging to the corresponding component in the solution vector, whatever vector we're looking at. For I equals, up to n. Okay, so are there any questions about distance between vectors or convergence of vectors?
What do you call component-wise convergence?
Do what?
Like, is it?
Yeah, so this would be component-wise convergence. And it can only be true that a vector converges to another vector if we have component-wise convergence.
Then what's uniform?
Uniform convergence?
Is that something different?
Oh, I'm not sure what you're talking about. Yeah. It might be uniform convergence, might be just this, but I'm not sure.
Every component converges, so it has.
Right. So this is something that would actually be checked, and it means, and if this is true, then your entire vector. So that may be what did you say? Uniform convergence. I'm not sure about that term, but it may mean this convergence right here. Okay. So, and this is due to the fact that any vector norm, then the only way we get this is if it's equal to the 0 vector. So that's why we have this component-wise convergence. So now that we've defined convergence with respect to an arbitrary norm, it's important to know whether a sequence can converge to a limit with respect to one norm while converging to a limit and another norm, or perhaps not converging at all. So maybe we have convergence in one norm. Does that mean that we also have convergence in a different norm, maybe the one norm or the two norm? So that's important to understand the relationships between the convergence of these norms. If you're using the one norm, you want to also make sure you know how it relates to the two norm, the infinity norm, and so on. So fortunately for the p norms, it's never the case where we'll have convergence in one norm and no convergence in the other norm. Okay, I'm going to go ahead and write. when we're dealing with P norms, we'll never have a case where we get convergence in one norm and we don't have convergence in another norm. So we can say that two vector norms, like one norm alpha and one norm beta, are equivalent if there's this a constant, which we'll call C1 and C2, that are independent of X, such that for any vector x, then we have this expression. So C1 and C2 alpha. Alright, so we've got these two norms, alpha and beta, are equivalent if there's constant C1 and C2. If we have this statement right here, so if alpha, C1 and C2, then these two norms are going to be equivalent. So if the two norms are equivalent, then a sequence of vectors that converges to a limit with respect to one norm will converge to a limit in the other norm as well.
Wait, what's the same limit?
Well, we'll take a look at some examples in just a little bit about that. So, let's see. Let me sum that up. So, let's see. Always has two norms are equivalent. Then a sequence of vectors that converges to a limit in one norm will also converge. Yeah, will converge to the same limit, actually. So it is that it converges to they both converge to the same limit. So what we're saying by this is that all LP norms are equivalent. You just may have a preference over which one you use based on what you're working with. So if we have all P norms are equivalent, then we also have these three inequalities. So we have the two norm is less than or equal to the one norm of x is less than or equal to the square root of n and the 2 norm. So the 1 norm, this is the inequality that we have for the 1 norm and the 2 norm comparing these two. So the 1 norm is going to be in between these right here. And then for the infinity norm and the 2 norm, we have the infinity norm is less than or equal to the 2 norm, which is less than or equal to the square root of n, as the infinity norm of x. And then the last inequality is that the infinity norm is less than or equal to the 1 norm, which is less than or equal to this. Just says n in the notes, but I think it's supposed to be the square root of n for the infinity norm. So these are useful sometimes too in various proofs. So now that we've talked about vector norms, we can also discuss the same concepts for matrices. So now we're going to go on to matrix norms.
Can we not interchangeably use the 1 norm and the 2 norm, because the last 2 lines are essentially the same, right? Like you just replace the 2 norm with the 1 norm.
Infinity, I see what you're saying, the 1 norm with the 2 norm. Well, I don't have these inequalities derived here.
Should there be a difference, or just like something that makes it easier?
Maybe it is that it's just n instead of the square root of n. So I'll need to check and see if there is a typo in the notes or if it's actually just n. Because in this case, it wouldn't
That's different.
It wouldn't be the same. So that's probably what it is. I'll check and see. Okay. All right. Erase this board. Alright, so like I was saying, now that we've looked at vector norms, we also want to look at the matrix norms. And so this will be useful because we can measure the magnitude of a matrix or the distance between two matrices. But it's not sufficient to simply define the norm of an n by n matrix as the norm of an mn vector, whose components are the integers of A. So we have different definitions for these matrix norms that correspond to the vector norms. So the matrix norms okay. So if we have a norm, we have these properties, and they're similar to the vector norm. So a matrix norm is going to be greater than or equal to 0, where A and then A is only equal to 0 if and only if the matrix A is just 0 matrix. So that's our first property. And then our second property corresponds to the vector norm. So if I have a scalar times a matrix, then I can just pull the absolute value of that scalar out and multiply by the matrix norm of A. For any n by n matrix A, and any scalar alpha. And then lastly, of course, we have the triangle inequality for matrix norm. And it just says that if I have the norm of A plus B, then it's less than or equal to the norm of A plus the norm of B for any matrices A and B. So these are the three properties of matrix norms, but we also have another property for matrix norms, and it's not always included in the definition, but we'll go ahead and include it here. And this is, on the fourth one, if A is an n by n matrix, B is an n by p matrix, then the norm of A times B is less than or equal to the norm of A times the norm of B. And this is what we call the submultiplicative property. So these are the four properties of matrix norms that all matrix norms have to satisfy. So this last one is particularly useful when A and B are square matrices. So now, as I was saying, we have vector norms and we have matrix norms, but another thing we can say about the relationship between vector and matrix norms is that any vector norm induces a matrix norm. So if we have a vector norm, then it's going to induce a matrix norm.
You have to know if induces a matrix norm?
Do what?
Induces a matrix norm.
Yeah, so any vector norm that we have induces a matrix norm. So if I have a vector norm, like a 1 norm, 2 norm, or infinity norm for a vector, then it's going to have a corresponding matrix norm that goes along with it as well. But we have other matrix norms too that are not necessarily induced by a given vector.
Well, yeah, I actually found it out online. It is N.
It is. Thank you very much. So this right here was N. I just said that any vector norm induces a matrix norm, and it can be shown that a given vector norm defined appropriately for m and n vectors. So if we have a given vector norm, or this is a matrix norm, so given any vector norm, that's defined appropriately for m vectors and n vectors, then we have the function, and this is defined by, so this is our matrix norm that we have here, and it's defined by this. So it's going to be the minimum of x not equal to 0 over x. So this is just the maximum of the norm AX. So this is our definition for a matrix norm in general. And then we'll talk about each specific type of matrix norm as well. So this is a natural or induced norm, and this is how we get our matrix norms from the vector norms. So furthermore, if the norm is an LP norm, then the induced matrix norm is going to satisfy the submultiplicative property. So I guess I should say induced matrix norm. Okay. So now we're going to take a look at each specific type of matrix norm, just like we did for vector norm. Yeah, so we'll have to remember here for this. So the first one is, of course, going to be the L1 norm. And so, based on the definition, we have the L1 norm of matrix A, and it's going to be the maximum of X equals the 1 norm, or the 1 norm of X is equal to, so this is the unit vector, and then A at the 1 norm equals the maximum from J equals 1 to N of this sum I equals 1 to M of Aij. So this is the L1 norm, and we can just take a look at this right here. And the L1 norm, so it's the maximum from J equals 1 to N, so we said the L1 norm is the maximum column sum of A. Is a good way to remember it. So it's the maximum column sum of our matrix A. And so to see this, we're going to let X be a vector in Rn that is a unit vector. So we have the 1 norm is equal to 1. So we want to look at the norm of AX. So the 1 norm of AX is a sum from I equals 1 to M AX I. So we have this by the definition. And now, if we take a look at how we define A, then we can have two sums. So I equals 1 to M, J equals 1 to N of Aij Xj. So now, I can pull this sum, the sum over J out front, and I can pull X out with it because X is not dependent on this sum over I. So this is going to be J equals 1 to N of Xj, and then I equals 1 to M of Aij Alright, so now the next thing that we can see is, so this is taking a look at each column sum over J, but this is obviously going to be, so if I'm looking at each column sum, then if I find the maximum column sum, then that's obviously going to be greater than each individual, greater than or equal to each individual column sum. So I have this inequality greater than or equal to, so J equals 1 to n of xj. So now instead of looking at each column sum, we're going to be looking at the maximum column sum. I to n aij. Alright? And now, but by the way that we've defined this, because we're trying to arrive at the one norm, or the definition that we have for the one norm, this has to be less than or equal to just the maximum column sum, because what did we define x to be? Up here. What is the one norm of x equal to? 1. So it's the unit vector. So this is going to be less than or equal to the previous statement because this is just the unit vector right here. Aij. The maximum, yeah, okay. So, now, so we've gotten from the one norm of a times x, where x is the unit vector, to the definition that we wanted for the one norm of a matrix. Now, this is less than or equal to, but equality is achieved. Go right here for this. So equality is achieved if the vector x is equal to ej, where the index j satisfies the following. It's the maximum over j, and then we have I equals 1 to m of aij. Aij. So that's what this index j has to satisfy right here. So that's when we'll have equality with this matrix norm. So it follows that the maximum column sum of A is equal to this expression right here, AX in the one norm, where X is as we've defined it. And it's taken over the set of all unit one norm vectors. So that's what we have here. So now we've just shown that the matrix one norm is actually the maximum column sum. So that's the induced matrix norm for the one vector, and we also, for the one norm, and we also can look at the two norm and the infinity norm as well. So we've looked at the one norm. Now let's look at L infinity norm. And the definition of this norm. So if I have the infinity norm of A, it's going to be equal to the maximum which is equal to maximum over I equals 1 to n of aij. So with the one norm, I had the maximum and I was looking at the columns, so now what I'm looking at is the rows. So we can say an easy way to remember this would be that the infinity norm is the maximum row sum of a matrix. So
is it 2 norm the diagonals?
do what?
Is it 2 norm the sum of the diagonals?
No.
It's quite a guess.
Alright. So we have a maximum column sum, maximum row sum, and this formula can be obtained in a similar manner than what we did over there. So now, Abdullah will look at the 2 norm. So if I have the 2 norm of a matrix, maximum of this, I keep doing that. So it's the 2 norm of those, equal to 1, so we have the unit vector. This 2 norm. Now this one is going to be a little bit different. So what we want to do to obtain a formula for this norm is, first of all, we're going to take a look at the function g of x. And we're define it to be the 2 norm squared of a over the 2 norm squared of x. And so this has a local maximal or minimum whenever x is a unit L2 norm vector. So when x unit L2 norm, or we say the norm, the 2 norm of x equal to 1. That satisfies this equality right here. So A transpose A times x is equal to the 2 norm squared of A times x. Alright, so what does it look like we're going to be dealing with now from this right here? Well, it can be shown by differentiation of this function g of x, that can be shown by differentiation of g of x. So what this is saying is that x is an eigenvector of what?
A transpose A.
Right, so x is an eigenvector of A transpose A.
Eigenvalues will be the diagonals of.
Well, yeah, so here we have the corresponding eigenvalues.
Supposed to be at 1?
Mm-hmm.
Yeah, right.
Right. So and that is equal to g of x, because here we have x2 is the unit vector. So now from this we can conclude that the 2 norm of A is equal to the maximum I is 1 to n of the square root of the eigenvalues of A transpose A. So we have the square root because here we have the 2 norm squared, so we have to take the square root. So that's our definition for the 2 norm. And so obviously the 2 norm is going to be the most difficult to compute simply because we have to find eigenvalues to be able to compute the 2 norm. I said that the infinity norm is the max row sum, the 1 norm is the maximum column sum, and an easy way to remember this one is that the L2 norm is the square root of the largest eigenvalue of A transpose A. So those are all of our induced norms. We've had one induced from the 1 norm, 2 norm, and the infinity norm. We've got about 6 minutes left. So we'll go to the next norm. This one's actually not an induced norm because it doesn't come from a vector norm. Come back here. And so this last norm is called the Frobenius norm. In the Frobenius norm, the definition, the way we denote the Frobenius norm is we say, we just put an F there in place of whatever P norm we have. The sum from I equals 1 to m. J equals 1 to n, aij squared to the 1/2 power. So like I said, the Frobenius norm is not an induced norm. So any of the things that apply to the induced norms no longer apply to the Frobenius norm, but it is equivalent to the vector 2 norm in the sense that I have the Frobenius norm, then it's equal to the vector 2 norm, where x is obtained by reshaping the matrix A. Into a vector. And you can see how this looks similar to the 2 norm for a vector, because 2 norm for a vector is the square root of the sum of the squares. That's what we have here, the square root of the sum of the squares. So that's where this equivalence comes from, is that the Frobenius matrix norm is equal to the 2 norm in a vector if we just reshape our matrix A into a vector and then take the 2 norm. Alright, so we have the same type of equivalences. Like vector norms, matrix norms are also equivalent, and we have these relationships between them. So we have the 2 norm of A less than or equal to the Frobenius norm less than or equal to the square root of A squared. We have 1 over square root of n times the infinity norm less than or equal to the 2 norm less than or equal to the square root of m times the infinity norm. And then finally I have 1 over the square root of m times the 1 norm less than or equal to the 2 norm less than or equal to the square root of n times the 1 norm. So, but just, naturally from the definitions of the infinity norm and the 1 norm, we can see how these inequalities would arise. We would swap in m and n as we swap one's row sum and one's column sum. So let's see if we have time for an example. No. Okay. So we don't have time for the very last example in this B.11, so we'll do that example on Wednesday, and then we'll go on to talking about eigenvalues so we can get ready for iterative methods next week. All right. That's all for today.